So last time we briefly looked at linear search. In a functional language, it's a function that takes an x, the element, and a list, and returns a Boolean. So x cannot be in an empty list, so we return false, right? X might be very well in a non-empty list. In particular, if we have that x equals y, well, then we found x, obviously. Otherwise, we recursively search into the y's, right? Okay, so we can actually load that function. We can start searching. And it works, right? So you see it's pretty simple. There's also something going on here that I want to talk about a bit more today, namely type inference. Right? So you see that I actually didn't write down any type here. I mean, no function type, no signature of the function. This doesn't mean that this function doesn't have a type. In fact, it's really very properly typed. It just means that I didn't have to write it down for the type system to make sense out of this. So actually, when in an interpreter session, you can actually ask the interpreter to tell you the type that the function seems to have. So we just tell it, okay, what is the type of search? And it returns that type. So, I mean, I will not explain every little detail of this type today. It's too early because there are some elements in this type that are a little bit more advanced in terms of language features we know by now. But let me sketch it. I mean, first of all, let's for a moment ignore that part. That's essentially just a constraint, you know. But the core of the type here is this, and it says, if you give me an A and a list of A's, I give you a bool, right? So, and by convention, in a type, these strings starting in lowercase mean type parameters, right? So basically, we have a polymorphic type here. So this can be any type, right? While in fact it can't be an arbitrary type, and that's what this constraint is for. It needs to be a type for which we have equality defined, right? Because as you remember, we were indeed invoking equality like this. And obviously, there are types on which you have equality, and of course, there are also many types for which you don't have equality. For example, function types. How would you compare functions other than by text comparison, right? It's pretty difficult. And there are other types that are troublesome. Anyway, but this is sort of the type, and we will see many such polymorphic types today and also in the next lab. And actually the assignment that's going online today, or already went online? Yes. So the current assignment also involves polymorphic types of a simple kind. Okay, so this is our first function of today. So let's see. This is linear search. Now, with many algorithmic problems, there are different algorithms solving that problem. In particular, if you add some constraints on, you know, your input data, then you might be able to come up with a more efficient implementation. So linear search is presumably the most inefficient way to do search, right? I mean, let's just look at the algorithm. It's pretty obvious from this formulation that linear search may need to go through the entire list to find x, namely in the case where x is at the end, or actually just to find out that x is not in the list, it also needs to go through the entire list. So this is, you know, going through the entire list is obviously pretty dramatic, and there's better ways of dealing with search. It's called binary search. Right? So binary search is a little bit more interesting algorithm. Essentially, binary search means that A, you require that the input list is sorted, and B, then you can sort of halve the search space in each step. So, well, let's not look at this code here. Let's just do this from scratch. Okay? So the idea here is, well, we can leave this case there, right? This is a good base case. It's pretty hopeless to find anything in an empty list. But if we know that the list is non-empty, then let's assume somehow that, and now I'm showing you something, also something new. Let's assume that we can somehow split up the sorted list L. So again, L we now assume to be sorted, right? So all the elements are in the right order. So now we assume that we can split up L into the following things, namely basically some prefix y is 1, and the second half y is 2. Okay? So let's not bother at this point how we do this. Actually, by the way, we can make this program type checkable just by doing it like this. So we don't yet know what to do here, but we do it like this. We can actually see that this program still makes sense, I mean, to the type checker at this point, right? So you see, it works. So we are allowed to use this undefined to keep things undefined until further notice, until we know, right? Okay, but we assume that this is the first half and this is the second half. Okay? And actually, we assume that the second half is non-empty. We could also assume that the first half is non-empty, but we want to have essentially the element in the middle, right? We want to have the element in the middle between the first half and the second half. Okay? So therefore we do this sort of pattern matching. Now, since the list L is sorted, we essentially check, hey, X, are you smaller than Y? And if so, what this means is that X, if to be found, must be in this part, because the input list L is sorted, right? Therefore, in this case, we search only in this part, right? Now, what could also be is that X is greater than Y, and that means that we need to search in the second half. And if neither of these cases applies, it means that X equals Y, and we have found our element, and so we return true. Okay? So this is binary search. Binary in the sense that in each step we try to, we halve the input list and we continue only in one half of the input list, right? Oops. Okay, so now the trouble is, of course, we need to actually split the list into these sort of equal halves, right? And there's different ways of doing this. I mean, we could now write some complicated functions to do that, but actually I'm going to use some library functions. First of all, I'm going to try to estimate what the length of these lists is. So how do I do this? I take the length of the of the L list, right? And I divide it by 2. So this is integer division, what I'm using here. This means integer division. And the fact that I'm putting diff between these quotes means I'm using it as an infix operator rather than a prefix operator. But let's not bother about this. It looks good on the eye, right? So you put the division operator between the operands. Okay. So now what we do is, if the length of the list is going to be len, then we just take that number of elements from the list, and here we just drop that number of elements from the list. So take and drop are some nice library functions that operate on lists. So take means, well, I can show you in the interpreter. If you say take two elements of 1, 2, 3, 4, 5, it obviously means that you take the first two elements, right? If you wonder what the type of take is, it's basically a number, the number of elements to be taken, the input list, and the resulting list. So what is drop? Drop is sort of the counterpart. It drops those elements and keeps the rest, right? So these two guys are obviously very handy when it comes to splitting this list here. So we just know how many elements should be in the first half, and we know that the remaining elements should be in the second half. And by the virtue of integer division, which might involve a remainder, it means that the second list might contain more elements than the first list. So if you think very hard about it, it means that the second list can never be empty, which is a good thing for this pattern matching, right? So one thing I haven't really explained, but you see it looks pretty intuitive, I guess. What we're doing here is we have local definitions, right? We say, okay, we want to have a variable wise1, and it should be defined like this. And actually, rather than defining this at the top like this, I'm defining it locally to the search function. So by having this var block, I'm allowed to have local definitions. Local definitions may access, of course, variables that have been bound in the enclosing block, right? So in this local definition, we are allowed to talk about the list that we are searching. Okay. So let's see. Seems to make sense, right? So if you look at the type of search, it's actually sort of almost the same type, except that now it says ord of A. So the constraint on type that we're searching on is that we have an ordering. Last time we were fine with just having equality for linear search, right? Now we need ordering by the nature of how binary search works, right? It assumes that the input is sorted, and we use the ordering to decide on whether to go left or right. Okay? So we can now search again. So for example, we can search, let's say, that works, right? Fine. 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 So now let's screw it up, right? This is a bad input. Well, but it happens, we are lucky, right? But you can probably, just as an exercise for you, you can probably find an input list that is not sorted and that will not find the element in the list even though it's in there. That's intended, right? This algorithm only works correctly if the input L is sorted, because it will not exhaustively look at all elements. Okay. I mean, overall, this is a nice piece of code in the sense that there are many things going on in here. So this is a good moment in time for you to recapitulate whether you are sort of fluent in the basics of functional programming, right? So you see recursion at play here. You see pattern matching at play here, like here or here. You also see how we use conditionals. And as I said, conditionals are always kind of total in the sense you must have a then and an else branch. Otherwise, you were not defining a function, right? And, well, you see how we use various library combinators, division, take and drop on lists, or lengths of a list, also library combinator. Okay? So while we are at it, we could also just program a little function to test whether a list is sorted, right? So let's write the function sorted. Sorted takes a list and should respond with true if the list is sorted and with false otherwise. So obviously the empty list is sorted. Good news. Well, we can go one step further. Actually, the list with one element is also sorted, right? Now, it gets a little bit interesting. The list with two elements is sorted. Well, if certainly x is smaller equal y, well, we don't need any if. That's one requirement, right? And moreover, this list must be sorted. All right? So basically, we check the first pair. If the first pair is in the right order, and if so, we continue with everything but the first element. As usual, we were not allowed to also remove that, right? That would be too much. So this is the right way to do it. Seems to be working. Type of sorted is we must have an ordering, otherwise it takes an arbitrary list and returns a bool, right? And this input here that just accidentally worked with binary search, this input is of course not sorted, right? But all the other inputs here, all the other inputs, they were sorted, okay? If you think about what is fundamentally necessary to operate on lists, then the following operations arise. You need the null operation. This is the operation taking a list and returning true for the empty list, returning false otherwise. Then what you also need on lists is, of course, the ability to access the head of a list, right? So it takes a list of A's, returns an A, and you also need the function tail, that's your question, to return everything but the first element, the tail, right? And actually we can also look at what is the type of the empty list. Well, it's some list type, right? And we can also look at what is the type of the list constructor for the non-empty list. Well, it takes an element A, it takes a list of A's, and returns a list of A's. So basically with these guys, you have everything you need in order to operate on lists. There's of course more operations on lists. For example, there's also the operation init, right? Init is actually the operation to return everything but the last element, right? There is in fact also last, which is the operation that returns the last element in a list. It just happens that these guys are presumably not as efficient as the other guys, and we might get into this, right? So sort of lists in Haskell are meant to be processed, if you like, from left to right, because this is how they are constructed. A head and a tail, which again is composed possibly. So we already have started to talk about sorting, right? Because we have implemented the sorting test. So what is the sorting problem? So sorting is basically the next most obvious problem that we might want to look at after search, right? So the sorting problem is that you have an input, again a list, and you want to get an output such that the output list is a permutation of the input list. So a reordering, a reshuffling of the input list, and the output is sorted. Sorted in a sense as we just have, written down, right? Sorted in that sense. So this is the sorting problem. So basically stated as a problem, it goes like this. Is it possible, to write an algorithm that given list of values to return a permutation of that list that is sorted. And of course, this is an algorithmic problem because there are plenty of sorting algorithms. Good news. So here's our, by the way, here's our sorted again, right? This is one part of the problem's description. And here's some complicated description of testing that one list is a permutation of another list. Let's just make a simpler one that sort of makes an additional assumption. So what does it mean for one list to be a permutation of another list? Well, okay, so we basically know that the empty list is a permutation of the empty list. That's easy. Now let's assume, so that we get a simple definition, the more complicated one is on the wiki page. Let's assume that no element occurs more than once in any list. So what we assume, what we check first is that length of L1 equals length of L2. Okay? And again, we assume that there are no doubles, right? Now, what we can simply do is we can try to search all elements of L1 in L2. Okay? What is search all? Well, if we have nothing left to be searched in some list, then we succeed. If we still have something to be searched for in L, then what we do is, well, we search, you know, using linear search, for example. We search X and L, and we also continue searching, right? So search X, blah, false, search X, Y, Y's. Wow, stupid. Okay? So this would be a test for permutations. I mean, if there are no doubles. Let's just see whether I got it right. That seems to work. That seems to work. Yes, and that should be false. So it seems to be fine. Okay? And again, it's a little bit more tricky to do the permutation test that is part of the definition of sorting if there are doubles. Okay, so we know now what the sorting problem is, right? So now we want to see algorithms, actual algorithms for sorting. And we are going to see 4 sorting algorithms. I mean, usually this would be impossible if we were using Java, right? Because, you know, we couldn't quickly enough go through all these options, and I couldn't write all the code. But, you know, for Haskell, this is just a no-brainer. So let's start with insertion sort. Well, there's actually nice illustrations on YouTube how all these sorting algorithms work. It's based on some folk stance, right? These are the elements to be sorted, but anyway, I mean, let's not bother. Shut up. Yep. So insertion sort. Let's go to the citation from Wikipedia. Insertion sort basically works by inserting repeatedly elements from the as yet unsorted input into an emerging sorted output. So basically you start with an empty sorted list and you continuously insert another element into the right place. That's how you can do sorting. So it's pretty easy to write down. So sort takes a list and is supposed to return a sorted list. And insertion sort works by performing many insertions. Namely, it needs to insert all those elements, and it starts with an empty list in which to insert. So, how does inserts work? Well, if there's nothing left to be inserted, then the output list as it stands is just fine. If you have another element to insert, then you have to actually insert it. So this is now a helper function to perform a single insert. So you insert x into L. And when done with that, we need to perform the remaining inserts like this. Okay? Now, if you have to insert x into an empty list, that's easy enough. We just build the list. If you have to insert x into a non-empty list, then different cases need to be considered. Namely, if x is smaller or equal y, this means that x actually belongs in front of everything we have. Right? So then we just return x followed by y followed by y's. If x is greater than y, then y needs to get in front. And we need to recursively insert x into the tail of the output list. Okay? And that's the entire algorithm. So if you have not yet done this in Java, I think your brain might still be wired in the right way. If you already have done Java, I think you see now, well, what beautiful things have been hidden from you. Okay. So we sort, for example, 1, 2, 3. Seems to work. Seems to work. Okay. So we will look into testing next time. How should we properly test such algorithms, right? We will do this in the next lecture. Okay, so this is our first sorting algorithm. Pretty simple. Okay, so now there's many sorting algorithms. Let's consider the next one. Right, so we can go here, sorting algorithm, and you see, well, insertion sort, merge sort, quick sort, selection sort. These are the guys covered on this wiki at this point. So let's see what's next. Well, we want to do quick sort. Quick sort is also a very famous sorting algorithm. Quick sort also allows us to talk about a class of algorithms that's called divide and conquer algorithms. A divide and conquer algorithm is one that essentially breaks down a problem into parts and recursively solves these problems. So it's more than recursion. It's, I mean, insertion sort is obviously recursive, right? It's about the fact that you take, for example, an entire list, and you break it up into two parts, into two halves, and then you recursively go into these lists again. Okay? So there is this quick sort. So quick sort, let's just see how it's described. So and again, there's a nice video, but so it works basically by dividing an input list into two lists, namely the, as they call it here, the low elements, let's say the small elements, and the high elements, the great elements, okay? So we just need to figure out how we know what are the low elements and the high elements, and that we sort of do by just picking some element, it's called a pivot element, according to which we set up these two halves. Well, let's just start coding right away. It's too easy. Sorting the empty list is easy. Sorting the singleton list is easy. Sorting the other kind of list, well, let's say what we do now is we assume that this head of the list is going to be our pivot element, the element that we use to get low elements and high elements, okay? So we want to get somehow low elements and high elements, okay? And we will see how we do this in a second. What we do then is we recursively sort the low elements. We also somehow recursively sort the high elements. And now we need to put x in between. And this means concatenation. So we have a sorted low list, we have a trivial list in between, and we have a sorted high list. Okay? Now we still need to figure out how we get the low elements and the high elements. And I just forgot, yeah, I'm using sort of sophisticated style here. That's not good. So, you know, I don't want to yet explain in detail what we are doing here. This is already a little bit more sophisticated. We use higher order functions. Don't want to explain this today. I mean, if you want to go faster than in this lecture, fine. But I'm trying to do this with simpler idioms. So we want to have we want to have the low elements. So what we could do is we could say, we write a function less than, right? And we want to get all the elements from x's that are less than, let's just say less x's. And here we say greater, but we actually mean greater equal, okay? So if we have an empty list, well, we return the empty list. If we have x and y and y's, then if y is less than x, then it should be in the resulting list, right? Then we return it, and we recursively determine the other elements that are less than y's. Else, we skip y. Okay? So obviously greater could just be defined by flipping around this guy here, right? Well, we should probably, if we assume that there are doubles in the list, we should replace we should replace less by greater or equal than. Anyway, so this is how quicksort works, right? So you divide the input list, x's, into low elements and high elements. You recursively apply sorting to it, and you recompose the intermediate results through concatenation. And of course, we shouldn't forget about the pivot element. Well, I should probably just really complete this example. So let's see. We can just reuse all the test cases, right? Seems to work. So how do you see that this is a divide and conquer algorithm? Well, very simple, because you really have multiple invocations of the sort function here on sub-problems, right? I mean, it's not just plain linear recursion, as we call it. It's actually binary recursion here, in the sense that you really apply the sorting function to parts of the problem, and you somehow compose the intermediate results. So by the way, if you want to know what the type of plus plus is, it takes two lists and of course returns a list, right? So I think you have seen everything else in this code. You see that this is of course boring code, right? I mean, in a way, how we walk over the list and how we try to find elements that are less than or greater or equal than some other element. So actually, ultimately, we will not need to write such code anymore, because we just know where to find appropriate library functionality to do this as shown on the wiki page. So if you go to the wiki page, you know, it uses much more clever idioms to actually achieve the same thing. Okay, but we will not explain this today. So, let's do some more sorting, because sorting is so much fun. Merge sort, it's actually another divide and conquer algorithm. It's this kind of algorithm or this kind of approach that really makes you understand recursion, if this is still necessary. And I mean, it looks much more beautiful than in an imperative programming language, as you see in a second. So what is merge sort? Merge sort basically means, well, you see again the simple cases. That's obvious. But what it basically does, it basically just splits the input into two halves, and it just recursively sorts them, right? I mean, okay, let's just write it down incrementally. Okay, I mean, obviously, we always have this, right? We need that as a base case, because all these algorithms are sort of de facto recursive, so that's a good one to have. It can't hurt to have this one. Perhaps we don't need it, right? But it can't hurt to have it. We can actually try later whether we need that case, okay? But merge sort now says, okay, if you've got a list here, just split it into two parts, you know, basically the first half and the second half. And then you just sort the first half and the second half. Well, but now we need to be careful. How do we combine the intermediate results? We cannot just concatenate them as we could in the case of quicksort, right? In the case of quicksort, because we put low elements on one side high elements on the other side, we could just concatenate the recursively sorted lists. Here, we actually have to merge them. Merge in a sense like a zipper. We need to take one element from the left, if that one is the small one, or from the right, if there's the small one. Okay? So how do we split? Well, splitting is easy. We already have seen this, how we split for binary search, right? So this is how we split. How do we merge? Well, if we have an empty list here on one side and whatever on the other side, then there's nothing left to be truly merged, right? We just return what's on the other side. If we have something here and an empty list there, again, we just return that remaining list. Okay? So now we are down to the case that we have non-empty lists on both sides. Okay? So how do we merge? We want the resulting list to be sorted. Well, if x is smaller equal y, then we put the x as the first element in the output, x, colon, and then we continue with merge x's okay, else it's the y that needs to go first. And we do it like this. And so this is the merge sort. Okay? Well, not too bad. Seems to work. Seems to work. Also fine. Yeah, I should probably have shown this nice zipper kind of thing, right? Let me see whether I can find it on the spot. So basically, merge really works like a zipper, right? Except that it's kind of a, not completely symmetric zipper, right? I mean, because there might be 2 elements coming from left and then 5 elements coming from the right, right? So it's not like exactly 1 from the left and then 1 from the right. But other than that, it feels like a zipper, okay? So now we were actually discussing whether we need this case. So we can just try, right? Why think? Aha. Okay. It seems like we need it, right? So let's see where we are. I mean, now what I want to do is I want to play a little bit with this sorting and list processing idioms in the context of the 101 company system. Namely, there is a feature in the system which is called the median feature. It's about computing the median of all salaries. You have all salaries, and you want to know, when you sort all the salaries, you want to know what is the salary in the middle. You could also compute average, right? So you basically sum up all salaries and divide them by the number of employees. That's average. When you go for the median, then you want to know the salary in the middle, right? Just a nice feature. So this is like when you want to talk to employees, during performance interviews, for example, and you want to tell them, you know what, don't complain, your salary is actually above the median, right? Because this means you get more than what half of the people in the company get, right? And that makes you feel good, and then you go home and don't complain. Okay? So remember this sort of code here, Haskell starter. Companies are pairs of company names and employees. Employees are triples, names, addresses, salaries. Names are just strings. Addresses are just strings. Salaries are floats. This is how our sample company looks like. So obviously we've got a few employees here. We can now total all the salaries. So actually I changed the code compared to last time. So we total all salaries by, well, retrieving all the salaries, a list of salaries, and then applying the sum function to it. So did I actually explain function composition last time? I forgot. I think I didn't, right? So, you know, we were talking about function application, function definition. I mean, in a sense, we were saying that the most basic idiom of function programming is function application, right? You apply a function to some arguments, and then, of course, you evaluate that function application, and that's how you compute things. But actually, as you probably know from mathematics, you can also compose functions, right? So what we do here is we compose the function to retrieve all salaries. So this is the function to retrieve all salaries. You compose it with the sum function, which means you first apply this function and then you apply that function to the intermediate result. So yeah, let's just study this code slowly again, but just to see where it's going. So you see there's also the median function here. The median function also retrieves all the salaries and applies function composition to sort all these salary values. And then it applies a new function, which I called median sorted, to actually compute the median, the salary in the middle. Okay? Let's first understand this code again. So this code basically retrieves all the salaries from companies, right? And we have three functions because we operate at three different levels. We operate at the company level, at that's this one, and we operate at the level of lists of employees, and finally we operate on individual employees, okay? So, and this bunch of functions here just essentially traverses over the company and over all the components and retrieves all the salaries. So here here you see how we actually, you know, compose all the salaries that we get. So we get a salary from the single employee E, and we compose it with the salaries of the remaining employees, okay? And this is how we get the salary of an individual employee. Well, we just pick up the right part of the triple, right? So it's not the name of the employee, it's not the address. No, it's of course this third component, which is the salary. Okay? And you see how it works. So basically total sums up all the salaries. Likewise, median sorts the salaries and then somehow tries to find the element in the middle. Okay? So let's see. We want to write this function here. We want to write this function. So assuming that we've got a sorted list, we want to find the element in the middle. So if we have an empty, empty list, it's pretty hopeless. So now we see the case of a function which cannot be usefully defined for an empty list. So what we could do is we could just leave out that case. Well, let's do this for now. Let's not define a case for the empty list because we simply don't know what to do. Okay? So if we have a particularly simple case is if we have only one element, then this is the element in the middle. Simple enough. Okay? Another particularly simple, well, is it simple? Let's say simple case is that we have two elements. And now there are different definitions of what the median should do, but usually the idea is to take the average of those two values. Right? So if there is no element in the middle, you can't pick it, well, then you take the average of the two remaining elements. So now we need to say what to do otherwise. And that's a little bit tricky. Well, one way of doing it is to say, this cannot be an empty list. This cannot be a, well, it certainly shouldn't be an empty list. It cannot be a singleton list, and it can also not be a list with two elements. So let's just then remove one element in the beginning and one element in the end and recurse. So that's what we do. We recurse into the tail of L and in fact the init of it. So back to the example. So here's the sample company, right? So now we can apply all our functions. We can apply salaries to the sample company. So by the way, you have tab completion in the interpreter, right? Just in case you didn't know, it's very nice to use. So these are all the salaries in the company, right? So we can also compute all the totals, well, the total of the salaries. And we can also compute the median. And why is this the median? Because if we apply sorting to all the salaries, then we obviously get 1, 2, 3, 4, 5, 6, 7 elements. Okay, so it must be the fourth element then, right? This one. This is the median. Okay, so I think I'm almost done. Let me see. Just a quick wrap up. I mean, I think you have, these are the conceptual things that I have mentioned throughout the course, right? So you have seen how we can invoke type inference. I mean, Haskell is doing this anyhow, right? When Haskell checks a program, it determines the type of each and every expression anyhow. But we can even ask in the interpreter what that type is, right? That's essentially how you feel that type inference is possible in Haskell, that a type can be inferred. Type checking means basically that the types that we have declared are of course also checked, and that all the rules of the language, like that you can only apply certain forms of addition to certain types, like float, all these rules are also checked, right? And polymorphism means that you have these type variables in the signatures, like all these list functions are typically polymorphic in the element type. And actually all these rules about how to apply operations correctly, how to form valid expressions in Haskell. That's called the type system. And finally, you have seen the local scope feature that you can have definitions that are local to other definitions, right? So this is basically everything that we studied today, and that's it. And next time we do essentially some software engineering for Haskell. Okay?